All right, everybody. So, 8-3 is the converse of the Pythagorean theorem. So we know that if you have a right triangle, you can use the Pythagorean theorem to solve for any missing side, right? A squared plus b squared equals c squared. So cool. But did you know that not only can you use Pythagorean theorem to solve for a missing side of a right triangle, you can actually use it to tell if you even have a right triangle to begin with. So we all know the top one. If you have three sides of a triangle, and it is true that a squared plus b squared really does equal c squared, then of course the triangle is a right triangle. So if you are given three side lengths and you don't know if it's a right triangle, you can check it in the Pythagorean theorem and see if it actually is a right triangle or not. Now, if it's not, though, you can actually use Pythagorean theorem to tell you if it's an acute triangle or an obtuse triangle, based on how a squared plus b squared comes out in relation to c squared. So let's think about this one. C is always our biggest side, right? So if c squared is going to be bigger than a squared plus b squared, what kind of a triangle would you guess that would have to be? If you have this big old c squared.
Obtuse.
Yes. If your biggest side, C, think about it, right? If you have this big old third side, you're going to end up with some obtuse triangle. So that's the easiest way to remember this one. It's not really a hypotenuse, it's not a right triangle, but if your third side, the C is the biggest side, if that's so much bigger, it doesn't have to be so much bigger, anything bigger, then the triangle is an obtuse triangle. Because you just have this big third side. So when you square them and add them together, it makes sense that it would look something like that. So then naturally, if this is your third option, if a squared plus b squared really is bigger than c squared, what kind of a triangle must this be? That's it. The triangle is acute. That's it. That's all that, I mean, the most common mistake is just forgetting, okay, forgetting that that's obtuse and then this is acute. But if you just remember, oh, this big old third side, it's so big, got to be an obtuse triangle. So let me give you a couple to try. I'm going to try and trick you. I wonder if I'll catch any of you in my devil's snare trap. You never know when the trick is going to come. Let me zoom out a bit. So tell if the triangle, tell if the sides create acute, obtuse, or right triangle.
Is tell the first word?
Yes. Sorry.
No, it's fine.
All right, so we'll start off medium and then I'll throw the trick in somewhere. How about,
Why is there gonna be a trick?
why not?
Me and trick kind of like the trick or treat. Okay, that's it.
Okay, try these four. Hold on.
Wait, so is it A, B, and C? So 5 is.
You tell me. How do you
Oh,
know?
yeah.
I can't wait to hear these answers.
Oh, wait, 4.
Okay, are we ready? Do you need another minute? You ready to go?
So,
Okay, number one, what type of a triangle does that make? Obtuse. I agree. I'm gonna do this one out just in case you're like, I'm not really sure how you're doing this. So you need to test, first of all, you got to figure out who's A, who's B, who's C. It does not always go in order. Who is the one that's important, the most important? C, right? C has to be the biggest. A and B don't really matter, but C has to be the biggest. In this case, sure, it can go A, B, C, because 14 is obviously the biggest of my 3. Okay, so make sure you're putting in the biggest side for C. If you're not, you're automatically going to get it wrong. Well, I shouldn't say that. You might get lucky, but it's probably going to be wrong. So anyway, C is the biggest in this case. So I'm checking. How does 5 squared plus 12 squared? I'm going to put a question mark here because I don't know. How's it going to compare to 14 squared? I have to do the math out. So that's 25, 144. 14 squared is 196. When I add 25, 144, I get 169, which is less than 196. So since my C squared is bigger, according to our list here, that is an obtuse triangle. So if you have this big old third side, obtuse. All right, so I agree with you all. That's what that means. Obtuse. I wonder if you fell into the trap for number 2.
Probably.
What's the trap? Did you even notice? Julia. Yes, 3 root 2 is bigger than 4. That's one of them. So you say to, by the way, because sometimes, right, you don't know what, I don't know what 3 root 2 is, but my calculator sure does. So I just turn it into a decimal. It's 4 point something, 4.24. So then I'm like, oh yeah, okay, it's bigger. So sure, you can be A, you can be B, but this has to go in for C. If you did not put 3 root 2 in for C, I don't know. Now you're basically just guessing. Okay, so be careful. A squared plus B squared. I'm going to see how does that compare to, now be careful. I hope you squared 3 root 2 correctly. So this is going to be 9, 16. What is 3 root 2 squared? 18 is correct, right? Because it's really 3 times 3 is 9, and root 2 times root 2 is 2. So 9 times 2 is 18. So I get 25, which is greater than 18. So what type of triangle is this? That is an acute triangle. Number 3, tell me what type of triangle did you come up with for this one? Obtuse? Raise your hand if you got obtuse. Raise your hand if you got acute. Raise your hand if you got right. If you raise your hand at all, I got you. So bad. Tell them, what is it?
It can't be a triangle because the 2 smaller sides add up to that.
Oh, you can't even do this one. That is not even a triangle. Tricky. But now you know to watch out for that in the future. You should always be checking. If the 2 smaller sides have to add together to be something bigger than the 3rd side. And the last one. It's a right one. I hope you got this one. This one was like a gift. After I felt bad tricking you so bad. And I was like, okay, let me give this one. I gave you this one because I was hoping that you notice it's a 3, 4, 5. I just times them all by 3. See that? If you reduce them all by 3, you can basically just pull out a common factor, right? So you get 3, 4, 5. And we all know that the 3, 4, 5 is a right triangle. You don't even have to do the math. You certainly can, right? 81 plus 144 should equal 15 squared is 225. And lo and behold, 225, 225. Yay!
No, it's 3, 4, 5. You actually have to like solve it.
No. So that's 8, 3. So could you do that? So if I gave you, I think on the quiz, there's a couple questions just like 1 through 4. So you could do that? Perfect. Okay, I am gonna go on to 8-4 right now, which is probably one of my favorite sections in the whole, out of all of it. I don't know. I just love these darn things. All right, you ready? Special right triangles. You're gonna love these. Special right triangles. Why are they so special? Oh my gosh, wait till you see. Wait till you see. Let me see if I have, oh yeah, okay. All right, there are 2 special right triangles that we're going to learn about. The first one, you can create it by taking a square and just drawing in one of its diagonals. All right, so draw in one of the diagonals. It doesn't even matter which one. Tell me what you know about this triangle now. Obviously, that's a 90-degree angle because it's a square, right? Tell me other things you know. What kind of a triangle is that? It's a right triangle, you're right. Keep going. It's an isosceles right triangle, isn't it? Right? Because it's a square. So both of those sides, I'm just going to call them X. They have to be the same. So it's a right isosceles triangle. Tell me some more.
The 2 other.
Yeah, these 2 angles have to be the same. So that means they're both 45. Hence, the name of this special right triangle is called a 45, 45, 90. Yes, Carson.
Aren't they also both those triangles?
Yes, they would be. So this is our first special right triangle called the 45, 45, 90. So named because of its angles, right? So we know it's an isosceles right triangle. Cool. Turns out there's actually a really cool way. Like I already know the length of that diagonal without even like, I know it. I do. if these, watch this, you're not even gonna believe it. Don't erase this on your paper, but if these were side, give me numbers. 7, okay, if these were 7s, do you know what the length of that diagonal would be?
96.
Let's do it, okay? Let's assume, I don't know what it is. I'll call it Y for a minute. So if I'm trying to figure out what that is, it's a right triangle, so I could use Pythagorean theorem, right? Sure, okay, so let's try it. 7 squared plus 7 squared equals Y squared. Right, so that's 49 plus 49. 49 is what, 98? Square root both sides. That can split into 49 and 2, so wouldn't that just be 7 root 2? Okay. Well, that's interesting. Huh. So it's telling me that that's 7 root 2. Well, I mean, cool, so that worked for 7s. Let's say, so just for any generic one where it's X and X, let's say I was trying to figure out what that hypotenuse was. I'm gonna do the same thing. If I do X squared plus X squared, equals Y squared, I get 2X squared equals Y squared, square root both sides. What's the square root of 2X squared? X root 2, because I can pull out the X squared is a perfect square, so that would just be X root 2. So you mean to tell me, hold on, I hope you're understanding how cool this is. If I know one of the sides of this special right triangle, right? If I know just this one, right? I automatically know that one. And then the hypotenuse is just gonna be whatever the length of that side is times the square root of 2. That's it. Every single time that's going to be true. So let me find a piece of paper here. Let's wrap our brains around this. So you mean to tell me if I know I have a 45, 45, 90 triangle, which you do know if I just, that's all the markings you need, right? You know that that's good. I don't have to mark that they're 45 and 45. That would be literally, I could just do that, right? So if I told you that this was 8, what's this? What's this? 8 root 2. It's just that easy. Well, can I make it harder? Of course I can. What if I said, all right, well, what if this were 11 root 2? What's the side? 11, what's the side? 11. Okay, you ready for a challenge? What if this side was 2 root 3? The other one's 2 root 3, and the hypotenuse would be 2 root 6. You just take whatever the side is and times it by root 2. Right? Isn't root 3 times root 2 just root 6?
Yes. Yeah. Mathematically speaking.
Okay. So far, is everybody with me?
Wait, wouldn't that be root?
All right. Now, riddle me this stuff. What if this side were 10?
Root 5. That's what I was thinking. Oh wait, no, it's
5 root 2.
it's whatever makes 100. So whatever. Yes, I do.
So listen, 5 root 2 is the right answer. Now, so in order to get this side, right, if I know what this side is, I'm just going to multiply by root 2 to get this side. So if I need to go the other way, couldn't I just take this and divide it by root 2? Right? Right? I can take that number and divide it by root 2. So if I do 10 divided by root 2, you can't leave it like that. So times it by root 2 over root 2. You end up with 10 root 2 over 2. And yes, I can reduce those. And I end up with that 5 root 2. Yes. Well, watch this. Let's try this, and then you'll investigate your own question. What if this side had been, I don't know, 6 root 7? Now find those other sides. You're gonna do the same steps, right? That's why it's important to, I know some of them you can do in your head, but sometimes stop and ask yourself, okay, I'm just gonna take this number, I'm gonna divide it by root 2. Take that number, divide it by root 2, and then just do the math out, right?
7 over root 2. 3 root 14.
Right, simplify those radicals, so you get 6 root 14 over 2, and then just simplify. 3 root 14. Right, so if you have the hypotenuse, you need to divide by root 2 to get the other side. You get really fast at doing it in your head. So, but I want you to understand like where this is coming from, why you're doing these numbers. So hopefully that makes sense, right? If I would just take the side and I times it by root 2 to get the hypotenuse, to just go the other way, take that and just divide by root 2. So how do we feel about that?
Ain't bad. I mean,
I love the 45, 45, 90. It's so convenient. There it is. Okay, now let me show you our second special right triangle. We are going to take an equilateral triangle this time to create it. It's not the equilateral triangle itself. It's special in its own way. We don't usually refer to it as a special right triangle because it's not a right triangle, right? So what I'm going to do is I'm going to draw an altitude in there. When you draw an altitude, remember you go from a vertex perpendicular to it, the other side, and tell me everything you know about this triangle over here on the right.
all the angles are equal.
Ooh, well, the original triangle, all my angles were the same, but now for just this little one here.
It's a, what's it called?
It's a 30, 90, 45.
40, 45, 90.
Two of them are right. It's a 30, 60, 90. How? Well, remember in an equilateral triangle, they're all 60s, right? But then what happens to this angle up here at the top? It's getting bisected. So we end up with this 30, 60, 90 triangle, it's called. 30, 60, 90. Okay, so I'm going to draw it a little bit bigger so we can talk about it. A 30, 60, 90.
That equals 180.
True.
Baseball board.
All right, so here is the super cool pattern on the 30, 60, 90. Well, actually, hold on. Let's go back a little bit. Go back to your original equilateral triangle, right? If all the sides are the same, let me use some numbers and then we'll do it with variables. So if this were, gosh, I don't want to give everything away. Well, what happens when this altitude, what does the altitude do to this third side? It does bisect it because you basically end up with two congruent triangles here. So we can say that this right here is the midpoint. I'm going to call just 1/2 of that bottom, so just the bottom of this one triangle, X, which would mean the length of the whole side of an equilateral, of that equilateral triangle would have been how long? 2x. So wouldn't that be the same as the hypotenuse of this triangle? Because isn't that one whole side of the original? So if that bottom is X, the hypotenuse is 2x. And now you could do Pythagorean theorem to come up with an expression for this middle side. Anybody want to take a guess what it is? So in the last one, we took the side and we times it by √2. This time we're, or why don't you figure it out? Go ahead, tell me. Actually do it out. So call this y for a second. Do Pythagorean theorem and solve for y. Yes,
Why are we doing 30 minutes? Of tonight?
what do you mean? Oh, these aren't minus. This is just the name of the triangle.
Oh,
It's called the 30, 60, 90 triangle. Try and find me an expression for the altitude of that equilateral triangle, basically. So plug it in as y into the Pythagorean theorem and solve for it, and you should come up with an expression in terms of x.
I don't know if this is right.
If
I
it
got
did,
X-
then you'd have a 45, 45, 90 triangle.
If, I don't know if this is right, but X root 5. No, and so.
X √3, yes. So we're going to take whatever that side is, and we're gonna multiply it by the square root of 3. Yes. So here's basically when you are setting up your special right triangle, the side across from the smallest angle is the smallest side, right? Right, across from the smallest angle, the smallest side, you remember that? My smallest angle is 30. So the side across from the 30 always has to be the one that we call x. The hypotenuse will always be twice as big as that. And you guys just found an expression for the altitude. This one right here is always going to be whatever that short side is times the square root of 3. So that side is just x √3. That's so cool. I know. Let's practice some a little bit, okay? So it might be helpful to, yeah. I'm going to draw both of our triangles again fresh. Zoom out a bit. We can actually see everything. There we go. Oh, geez. There we go. All right, so my first triangle is the 45, 45, 90. I know because it's marked as such. So the sides we just call, you tell me, what do we call the sides? X. They're both X, and then the hypotenuse is just X √2. Okay, so there's the 45, 45, 90. Now in my new triangle, the 30, 60, 90, you do have to know which angle is the 30 and which is the 60. So I'll mark the top one as the 30, the bottom one is the 60. Okay, the shortest side, you call it X. And you know which one is the shortest, not because it looks like it's the shortest, because who knows what I'm going to trick you and have the numbers labeled in so that it doesn't match. You always go off of the numbers. Across from the 30 is going to be the side that's X. The hypotenuse will always be 2 times that. And then this middle side is going to be how long? X √3. You got it. Okay, let's practice a few problems with numbers on the 30, 60, 90. Oh, actually, before I move away from this, I have a way to try and help you remember how to draw these two. Because the most common mistake is that kids mess this up. They can't remember if that's the √3 or if that's the √3, or they get these two mixed up. Okay, you know, they each have a root something on it. Here's my way to try and help you. Remember, this one has 2 sides the same. So that's the one with the 2. 2 sides the same. That one's got the 2. This one has all 3 sides. They're different. That one's got the 3. Okay? Whatever you need to do to solidify in your brain that these are x, x, x √2, and this one is x, 2x, and that's x √3. 3 sides are different, so that one's got the √3. This one has 2 sides the same, so it's got the 2 in there. Okay, I hope that helps because you will want to be able to recreate these 2 triangles. Now let me give you some numbers with some 30, 60, 90s. Oh boy. We'll start off easy. Okay, let's try it. If I told you this side was 4. What's this side? 8. And what's this backside gonna be? 4 root 3, I'm hearing. It's whatever the short side is times root 3. See how that works? I have to give you one side to start with, right? So if I give you the short side, that's great because then you know, all right, I'm just going to double it to get this one. And I'm just going to take that same short side and times it by root 3 to get that one. Yeah, okay. Let me give you a different side. What if I had started with the hypotenuse? Let's say I gave you the hypotenuse is 10. You would start by finding the short side. The short side is 5, and then this side would be 5 root 3. Okay, not so bad. Could it get worse? Oh. What if the hypotenuse was 11? What's the short side? True. Leave it as a fraction though. Just call it 11 over 2. Right? You're not wrong, but just be careful. And then this third side would be, yes.
11 halves.
Yes. What are you gonna say? 11 over 2
11 seconds.
Okay. Miss Savia, that's not so bad. Oh, just wait. What if I did this? What if I said, all right, what if this side was 6? You do know. Think of what going the other way. What do you normally
The
do?
bottom would be 2 root 3, right? Then the top one. Not
Yes.
Yeah, bottom would be 2 root 3. The top one would be 4 root 3.
Yes. Where is this coming from? Now, think about what you normally do. Don't you take the short side and you times it by root 3 to get that? So if I need to go the other way, I'm just going to take that number and I'm going to divide it by root 3. So do 6 divided by root 3 real quick. And you very quickly come up with 6 root 3 over 3. Those cancel. We get a 2 root 3 for that bottom side. Again, the more you do this, the faster you get at doing that in your head. But that's the math behind it. You're just going to take that side and divide it by whatever the root is. Now that you know the short side is 2 root 3, you can find the hypotenuse. If I have 2 root 3 and I need the hypotenuse, all I got to do is, so I get 4 root 3. That's it. Right? Because isn't 2 root 3 times 2 just 4 root 3? Are you with me?
Yes, ma'am.
Everybody?
Yes, ma'am.
Yes.
Oh, good. You know what I should bring in, though I probably never will, but last year my in-laws got as a gift for my son, they're like these, it's bigger than a pom-pom ball, but it's like a whole bucket. It's like an indoor snowball fight. And so it's just like these white little, so you can just like throw them. Wouldn't that be convenient to have? And just, just as a friendly reminder. Hello, we're in school. Hello. Just a reminder to pay attention. Anyway. Where am I? So yes, I'm there. Okay, let me give you one more tricky one to try. And then that's pretty much it. So I'm gonna draw a fresh one. Let's make this one. How about if this was 5 root 10? Find me the sides, find me X and Y. Guess I should get the answers myself. Ooh. That's not so bad. Julia, you have answers?
Yeah.
Hold on to it for 1 second. I see a couple people still putting their pencil to paper. All right, Julia, go ahead. What'd you get for X? What'd you get for Y?
Just the 60s on the top.
I did another little trick. Oh, man. I put the 60° up there, which means this is the 30, which means X is the short side. Ooh. Ooh. You gotta watch. You gotta stay on those tippy toes. Watch. Be careful.
Like I got to that point where I was still checking to see if 30 was able to like any perfect squares or like, I was in the middle of
And I
doing
don't think that, yeah. So now we have, your numbers are right, just fine. So if that's my hypotenuse, this is now my short side. So I want to take this and I want to divide it by 2, right? Because normally I'd take the short side and I'd double it to get the hypotenuse. So let's divide by 2 to get the short side. So 5√10 divided by 2 does not simplify. I hope you were not trying to do anything like, I hope you didn't say something like 5√5. If you did, don't ever do that again. You can't do that. You can't reduce something that's in a radical with something that's not in a radical. So that would not be allowed. It's just 5√10 over 2. Now that I have the short side, I just need to take that short side and multiply it by √3 to get that middle side. And when you do that, 5√10 over 2 times √3 gets you that 5√30 over 2, which also does not reduce. You can't touch that 30 and that 2. Stop trying. They're not both in the radical. If one's in, one's out, you can't touch them. But that's it. Yeah. Go so fast.
You go fast at that.
Does this make sense?
Yeah.
Okay. I love special right triangles because you can do so much of the work without, I mean, you don't have to do Pythagorean theorem. It's all, if you know the pattern, you can get all your sides. Yes.
I'm not sure if I just plugged it into my calculator, but why would it be over 2 and not over?
Or which, for this one right here? Oh, for this one?
Yeah, so why? Like, yeah, that one.
So you're gonna take your short side and you need to times it by √3. You times it by √3?
Oh, I think I divide. Yeah.
Yeah, take that short side and times it by √3. The only time you'd have to divide is if you're given that middle side and I'm trying to get back to the short side, then I divide. But here, because remember we swapped these, right? So because this is my 30° angle, that's actually my short side. You can't go off of how the diagram looks. You gotta go off the numbers. Am I going to trick you? Probably. So you gotta be watching. You gotta be watching. Can you even make a triangle out of those numbers? If I'm asking you if they're right, acute or obtuse. You gotta be watching here, right? Just because it looks like a 30, 60, 90, you gotta look at how it's marked. Also, don't assume something is a 30, 60, 90 without knowing that it is, right? If I just give you this, you have no idea what that is. You don't know if that's a special right triangle. That could just be some random old triangle. So I need something to indicate if it's a 45, 45, 90 or a 30, 60, 90. So for 45s, I can just mark them as isosceles. But for the 30, 60, 90, I'd have to let you know somehow that one of the other angles is either a 30 or a 60. Okay, questions? All right, so let me see what I want you to do for homework tonight. But starting in class, since we have a good chunk of time.
It's not whole.
Well, my rule has always been, it is classwork until the bell rings, and then it transitions into homework.
I did my homework.
Well, you can, when it's classwork, though, you do it in class, right?
Oh, yeah, that's true.
So start there, bless you. All righty. Where's, I can't seem to find what I have, oh, here it is. All right.
6, 10. Wait.
Oh. Special rights. Oh, how I love them. Okay. There it is. I'll open that up in Jupyter in just a moment. Please let me know if you have any questions at all.
Four. Four. Got lost. So I gotta.